So the problem says we have 5 grams of aqueous ammonium chloride, so we really don't have to look up whether ammonium chloride is aqueous or not. Just turn over the chair, it's alright. It tells you in the problem it's aqueous, so I can say it's aqueous here. What? That's how I control the video here. Alright. And it's mixed with 5 grams of aqueous lead acetate, so we know that one's aqueous. I've saved you the trouble of looking it up. Lead is Pb. Acetate can be written in about 3 different ways, maybe 4 different ways. 3 are listed on the in the test references. I like to use this one. Okay. It says it's lead 2, so lead 2 has a 2+ charge. Acetate, if you look it up on the common ions list in your test references, have a 1 that has a 1 negative charge. So we need 2 acetates, and therefore we need to put 2 acetates in this formula. And it says it's aqueous, so we can show it to be aqueous. Okay? And then the question says 3 grams of a solid product is collected. So that's your product. That's what we're going to be looking for. We need to figure out what that product might be. So we're going to look at the problem and identify what classification of equation we have here.
Double replacement.
It is double replacement. I have a polyatomic ion here, so I've got an ionic compound. I've got a polyatomic ion here, so it's an ionic compound. When I have 2 ionic compounds, the most likely type of equation we're going to have at this stage in your chemistry career is going to be double replacement. So the front part of this compound goes with the back part of this one. This is a 1+ charge, and acetate's a 1 negative charge, so I need 1 and 1. Okay? And Pb is going to go with Cl. The front part of this one goes with the back part of this one. The front part always remains the front part. We need to balance it. Lead has a 2+ charge. Chlorine has a 1 negative charge. So to charge balance the formula, we're going to need 2 chlorines. Okay. Now one of these 2 has to be a solid. The question actually says you want to collect a solid. Okay. We need to figure out which one is which. If you look on the solubility rules, it tells you that all acetate compounds, and for that matter all ammonium compounds, are always soluble. So since there's water around, we know there's water around because these 2 are aqueous. That means they're dissolved in water. Since there's water around, anything that's soluble will be dissolved, so this is also going to be aqueous. Okay? If you look on the solubility rules, you'll see that chloride compounds are mostly soluble unless they're bonded with, among other things, lead. Lead 2. So this is going to be our solid here. So now that we know what our solid is, we know that when we do our stoichiometry, this is the product we're going to be looking for. We need to balance the equation first. Without a balanced equation, the stoichiometry will not work out. So we're going to list all of the elements we have. Nitrogen, hydrogen, chlorine, lead, carbon, and oxygen. A lot of elements here. Lots and lots of elements. I try. Alright, so we're going to start out. We have 1 nitrogen on this side. I have 4 hydrogens here. There's 3 hydrogens times 2 or 6 here. Let's make sure we do the math. Now, if you don't do the math and write down the math, you're just shooting yourself in the foot because it's really easy to make little silly mistakes, okay? Simple mistakes. And then 3 times 2 hydrogens is 6, so that equals 10. I see a lot of students make those simple mistakes. So just by writing it down, you can help prevent that. Alright, so we've got 1 chlorine. I've got 1 lead. I've got 2 carbons in the acetate times 2, so that means I've got 4 carbons. I have 2 oxygens in the acetate times 2, that's 4 oxygens. On the other side of the equation, I've got 1 nitrogen, and I've got 4 hydrogens here, plus 3 here, that's 7. Let's make sure we do the math here. 4 plus 3 is 7. Keep up with it. We've got 2 chlorines now. I've got 1 lead. I've got 2 carbons in the acetate formula. And I've got 2 oxygens in the acetate formula. Okay? Alright. So we're going to balance oxygen last, and we're going to balance hydrogen next to last. So I want to start with chlorine. That's a good place to start. So I have 2 on the right, and I want 2 on the left. I can only do that with coefficients. Once the formula is balanced, you've got to leave it alone. Okay, you can't stick any numbers in the middle of the formula. You can't change one part of the formula. You've got to change the number of the whole formula, okay, or the number of formula units. So I want 2 of these. That's going to change the number of nitrogens, hydrogens, and chlorines. So now I have 2 nitrogens. I had 4 hydrogens in the ammonium times the 2, that's 8. 3 hydrogens here times 2 is 6. So that's 14 hydrogens I have at the moment. And in chlorines, I now have 2 chlorines. Okay, so since I changed the number of nitrogens over here, I had to get it balanced over here. So I'll put a 2 coefficient in front of the species on this side that contains the nitrogen. And that's going to change the number of nitrogens and hydrogens and carbons and oxygens. So I now have 2 nitrogens, hydrogens. I've got 4 here and 3 here, 7 times 2. So of the hydrogens then I've got 7 times 2, right, basically, is 14. 4 plus 3 is 7, times 2 is 14, so it's 14 hydrogens. Chlorines, I've got chlorines balanced. Carbons, I've got 2 carbons in the formula, times 2 is 4. I've got 2 oxygens in the formula, times 2, that's 4. And everything's balanced. Okay? Now we're ready to start with the stoichiometry part of things, the mass-to-mass calculation. We're going to run 2 mass-to-mass calculations to find our theoretical yield, limiting reactant, and excess reactant. And we're going to need to find the theoretical yield to find the percent yield. Okay? We're going to start with the first reactant listed here, 5 grams of aqueous ammonium chloride. That'll be the first stoichiometry, and calculate to the amount of solid product. And the second equation, second calculation, we're going to start with the 5 grams of lead acetate and also go to the amount of solid product. Okay? Well, both times we're trying to find the solid product starting with one of the reactants. 2 reactants here. So I've got 5 grams of both of these. And I'm going to list on here that the problem says I've got 3 grams of this. Okay. Alright, so let's see, 5 grams, 5.00 grams of ammonium chloride. Put it over 1. I need to calculate the molar mass of ammonium chloride. Nitrogen, hydrogen, chlorine. Need the atomic masses of each of these elements. We find them on a periodic table. 14.0067 is the atomic mass of nitrogen. Hydrogen is 1.00794. And chlorine is 35.453. We're going to multiply these by the number of them we have in the formula. I have 4 hydrogens. And I want to keep everything lined up very neatly over here on this side. Alright, I've got a bunch of empty slots over here that are going to result in insignificant digits when I add everything up. So I'm going to add all these numbers together. Those two digits over here are insignificant because they came from or resulted from empty slots above them, and that's grams of ammonium chloride. We need to round that off then to the correct number of significant digits. 53.491 grams of ammonium chloride equals 1 mole of ammonium chloride. From this equality statement, we're going to build this conversion unit here. We want to match the units and species in the top with what we put on the bottom here. This side of that equality matches those units and species. The other side of the equality statement goes on the top. We're going to build a conversion unit, and conversion units equal 1. And this equals 1 because I have the same value on the top and bottom, just measured in a different way. By definition, the molar mass of a substance is the mass of 1 mole of that substance. And this equality statement basically states that definition for this particular species. Now, I want to cancel what I can cancel. And I want to get the molar ratio now. The molar ratio comes from the balanced equation. I'm starting with this species and ending with this species. So that's a 2-to-1 ratio. I'm going to put 2 moles, 2 from the coefficient, 2 moles of ammonium chloride down here. And 1 mole of lead 2 chloride on the top, because there's an implied coefficient of 1 in front of the lead 2 chloride. And now we can cancel these units and species. And we need to get the molar mass of lead 2 chloride to get back to the mass of that. Yep. What is what? Acetone? Why are you asking that question? Acetone in that case is a very important solvent to use when you do organic stuff. Kind of beyond the scope of this class. You don't really need to know the formula in this class. You would need to know the formula if you were taking an honors class. Okay, so now we have an equality statement, and from this equality statement we can build the conversion unit we need. We have moles left on the top here, so this time I want moles from this side of the equation on the bottom. You want to be able to match units and species top and bottom. And now we're ready to do this math. Okay. What I want to do is to take what's across the top and multiply, hit enter, then divide by what's on the bottom the first time, hit enter, then divide by what's on the second, divide by what's second to be divided by again, and then hit enter. So let me show you how that works. 5.00 times 278.1. I'm going to hit enter, and I'm going to hit divide, put in this number, 53.491 491. I'm going to hit enter, and then I'm going to hit divide by 2. Okay. Now some calculators will let you do the math a little bit more easily than others, but this seems to work for every kind of calculator and gets you through these stoichiometric calculations a lot faster. So I'm getting 12.9975.136. How many more digits do your calculators have? Just one? One more? 0? That's where it stops? My calculator just goes out to more digits. It doesn't matter. So we have grams of lead chloride, lead 2 chloride. Okay. We want to match the number of least number of digits in the measured and calculated numbers in the problem with what we have in our final answer. So we have 3 digits here, that's a measured number. 5 digits here, that's a calculated number. 4 digits here, that's a calculated number. The counting numbers like these right here don't matter because they're infinitely significant. We're not going to use those for determining significant digits. This number of the measured and calculated numbers has the least digits, so we want our final answer to have that same number. I'm going to underline everything after the first 3 digits then and round it off, and we get 13.0 grams of lead 2 chloride. Okay? Now that's the first of the 2 calculations. We're going to do another one now, starting with the other species, this 5 grams of lead acetate. Alright, so I need a molar mass of lead acetate. Lead, carbon, hydrogen, and oxygen. So lead is 207.2. Carbon is 12.0107. Hydrogen is 1.00794. And oxygen is 15.9994. I have 1 lead in the formula. I have 2 carbons in the acetate times 2, that's 4. I have 3 hydrogens times 2 is 6. And I have 2 oxygens times 2 is 4. Yes. Yeah, I guess. I mean, we got one more thing to learn, and then we're gonna be ready to start doing a test review. So I'm looking at maybe a test on Thursday.
No.
Okay, we got a bunch of empty slots here. And always did all these numbers up. And all the digits that result from empty slots above it get rounded off. This is grams of lead 2 acetate. Okay, and then we can take this equality statement and build the conversion unit we need. Want grams on the bottom here. And moles on the other side of the equality statement goes on the top. Cancel grams, cancel lead-2 acetate. We want a molar ratio from the balanced equation. We have 1 mole of lead acetate here, 1 mole of lead chloride over here, and that's what we're trying to go from, lead acetate to lead chloride. We're trying to get to the same substance at the end of this equation or calculation we're going on, we're calculating from a different starting place. Alright, so we got a 1-to-1 ratio here. 1 mole of lead-2 acetate and 1 mole of lead-2 chloride. Cancel. And now we need the molar mass for lead chloride, which we have already calculated here. We already have the equality statement. We're just going to plug in what we need. Again, moles here, that you put on the bottom to match the moles I have left on the top here. And the top will have the 278.1 grams. That's what we want to get to, is grams. Okay, cancel the units, moles, and the species, lead chloride, lead-2 chloride, and do the math. Okay. Alright, so we got 5 times 278.1. Enter, then divide by 325.3. And we don't have to divide by anything else because I've got all 1s on the bottom. Dividing by 1 just gives you the same answer. So I get 4.27451,583. And then, is that where your calculator stops? Or do you have another digit on there? A 2? Okay. So that's grams of lead-2 chloride. I'm going to round it off to 3 digits because this is the measured or calculated number here in the beginning. It has the least number of digits among the measured and calculated numbers. So I want 3 digits in this answer, round it off. I get 4.27 grams of lead-2 chloride. Alright. Now then, we're going to compare the 2 masses that we got for lead-2 chloride. Okay? I've got 13.0 here in the first calculation. Compare that to this one down here. And the smaller of the 2 numbers then is the theoretical yield. It's from the theoretical yield we're going to figure out what the limiting reactant is. So this is our theoretical yield. Okay, the species that was started with to get this number, that's our limiting reactant. That's this right here. Okay, so we have 4.27 grams as the theoretical yield, but this species we started with then is our limiting reactant. Reactant. Okay. The other species we started the other equation or calculation with, that's the excess reactant. Okay. So we've identified the theoretical yield. The theoretical yield is actually a number with a unit of measurement and a species. The reactants, excess and limiting reactants, are just the species themselves and not a number that is associated with it. So when we say what's the limiting reactant, we're not asking what is the amount of the limiting reactant. If I ask for what's the amount of limiting reactant, then you tell me 5 grams of lead-2 acetate. But if I'm only asking what is the limiting reactant, that's just the species lead-2 acetate. Does that make sense? All right. The thing we need to still calculate then, the last part of the question, is what is the percent yield here. Okay? Percent yields are really easy. We just take the actual yield, which we said was 3 grams of the solid product, and we identified that as being lead-2 chloride. We take that actual yield, 3.00 grams of lead-2 chloride. We put it over the theoretical yield we calculated. Okay. We're going to put all of that in parentheses and multiply by 100 to get a percent. Remember, percents are always part over whole times 100. Okay? And almost, I can't think of a percent, except some strange ones, where this doesn't happen. If you don't calculate the percent in a way that cancels out units of measurement, you probably didn't set it up right. Grams are going to cancel. Now, this particular kind of percent also cancels species, but doesn't always happen. What always happens, in this class anyway, for percents, is you will always cancel out units. Okay? So now we want to find the percent here for this. So 3.00 divided by 4.27, enter, then times 100, and we get an unrounded answer of 70, I'm sorry. I'm looking at the wrong number. Huh? I could. You're right. 70.257661124 is probably what you guys have. And that's percent. We want to round that off to the correct number of significant digits. In this case, 3. So we have 70.3% yield in lead-2 chloride. And that's our percent yield. Yes? Sure. Okay? Yep. I can. I don't have it ready yet, but I haven't printed it out yet, but I'll try to get it before the period's over if you want me to. Okay? All right. Wow. That's a lot of calculations, isn't it?
How many of these are going to be on the test? Like one maybe?
One maybe. Sure. All right. Now look, guys. Look. How many of you got the right answer? So, a handful of you got the right answer. And everybody else who tried are probably just finding, well, there's little pieces we're missing here, right? It's the little stuff that gets you. Sure, we'll try to do one more. Well, let's see. Wow, this took a long time to do this. I might just need to give you another practice problem. I need to teach you one more thing, which isn't very hard, okay? Not when you know how to do this, okay? This is, once you get all the details down, okay, you can get the answer, okay? Now, if I had shown you this at the beginning of this unit, said you're going to be able to do this, would you have believed me? No. But you can, right? You managed to get there. Imagine that. Imagine what you're capable of doing. All you got to do is have all the pieces together, okay? It's the little things that get you, okay? The little things that get you.